All right, welcome everybody to this week's installment of the Molecular ML Reading Group. Today we're excited to have Nima Shoghi, who's coming from Meta, the research team in Meta. And today they're going to be talking about pre-training large models to kind of capture more comprehensive molecular representations. So we're really excited to have them, and take it away, Nima.
Yeah, hi everybody. As I mentioned, my name is Nima. I'm no longer with Meta. But this work I did while I was there as a resident. I left Meta about September of last year. This work is going to be presented in ICLR in about a month. I worked with Adish Kolaru, John Kitchen, Zachary Ulyssi from CMU. Zach is actually a part of the OCP team now at Facebook. And then Larry Zitnik and Brandon Wood was the sort of senior sort of advisor that helped a lot in this process. Alrighty. The goal of this work ultimately is to create better ML models for chemistry in general, any kind of atomic property prediction, and so on, using pre-training. Um, Obviously, we want to accelerate discovery in material science, drug design. As I mentioned, I was a part of the Open Catalyst project, so they worked on finding sort of catalysts for sort of storage of renewable energy. But a lot of these same type of things could be applied to drug design, drug discovery, so on and so forth. Um, Obviously, ML is a great tool in these domains, and it can be used to, accelerate or approximate some of these expensive calculations that are necessary to to do these simulations. But ML obviously needs data sets to be able to, for us to be able to do these things. And these data sets are, they can be fairly expensive. And Just as an example, the Open Catalyst project, the first data set they released is the OC20 data set. That is a fairly large data set in this domain, but it took 400 million CPU hours to generate this data set. And it's really a type of work that I don't think any other sort of entity, maybe other than Facebook or Google, would be able to do. Um, and Pre-training has worked in other domains. So this is where the using pre-training parts comes in. In natural language processing and computer vision, pre-training has been a sort of useful tool for learning general purpose representations for the data distribution that you're working with, and then fine-tuning those models on downstream applications. So in the case of natural language processing, imagine if you're interested in a model that can give you do sentiment analysis, tell you if a sentence is positive, neutral, or negative, you could first do a GPT style pre-training, and then you would fine tune that model to do sentiment analysis. So what this allows you to do is essentially, even if your downstream data set of sentiment analysis is extremely small, that doesn't hamper your pre-training model's ability. Okay, so I'll just give like a high level overview of pre-training in natural language processing, vision, sort of traditional ML. So in these domains, self-supervised learning has been very successful. And ultimately what this comes down to is predicting parts of the input from, other parts of the input. Um, this is a process that sort of, enables learning from unlabeled data, and it's been transformational, as I mentioned, in these two fields. One example of this that I'd imagine at this point everybody's familiar with is language modeling. This is the type of thing that GPT does. So this is where you start with the context of all the words you've predicted so far, or have been given as a part of your context as the input, and then every time you're just predicting the next word in the sentence. This has been a key task that has led to a lot of success in NLP. Another sort of framework here is the mass data encoder framework. I've shown two examples here. One is in the computer vision sort of scenario on top, and then at the bottom is in the natural language processing part. This is where you mask out portions of the input and you predict the masked parts. And so in the case of BERT, what we see is you have a sentence and it's how are you doing today? And the U part ends up being masked, and the model is trained to predict that masked portion. And similarly, we see up top with a sort of vision transformer doing the same thing um, in the computer vision scenario. And then the other one that I want to speak of is the denoising autoencoders that are less popularly used as pre-training, but is definitely one of the methods for doing this. This is where you corrupt the input in some way, and then you predict the either the original input or the delta, or in other words, you predict the corruption that you've added to the ground truth. So the basic example up here is you take this two and you add some noise to it, and you train the model to undo the noise or predict the noise or something like this. In the NLP case, BART is um, one of the methods that used denoising as well, where they sort of, if you actually go look into this, they essentially change some words around and so on, and they train the model to figure out the cases where the words have been rotated or flipped or things like this in the sentence. Um, and more recently, you also see these diffusion models in sort of image generation, and those can be sort of seen as denoising autoencoders as well. And dating back to 2000, I think it was 11, there's been, there's a connection between these denoising autoencoders and score matching, which is sort of, it goes to the roots of some of these generative models, denoising models, so on and so forth. Um, so now let's go to pre-training and sort of this area of chemistry. Um, I I guess what I argue here is that we've had exciting progress, but we're very behind natural language processing and computer vision, provided like how much impact pre-training has had in those domains. And I think I guess the way I'll motivate this is by just going through. We in our paper we developed a fairly exhaustive a benchmark of 3D, you know, um, uh, materials property prediction, atomic property prediction, molecular property. Like we try to cover many different domains and many different downstream properties. Um, and if you actually go look through all of them, and these are the five main sort of benchmarks, tasks that or data sets that we work with. Um, Aside from QM9, which it was five of them were coming from models that were pre-trained. Every other task, the previous state of the art was from models trained from scratch. Um, so in total, that ends up being uh, actually it's six of them. So yeah, but 34 out of 40 tasks that we worked with, scratch models held the state of the art in them. So why is this? I think there's several key challenges, and there are some that seem like challenges that I'll argue are sort of non-challenges. And I'll start with the ones that I don't think are, uh, uh, I think are the non-challenges, and then I'll go into the ones that I do think are more serious. Um, so first, I'll just go through ones that weren't even a part of our, part of our study in this work. And one clarifying term about this non-challenges term. Um, I think these are important challenges. It's just I don't think they're blocking challenges for having successful pre-training in this domain. I think there are potentially ways to get around them. Um, uh, so one is architectures. In natural language processing, transformers have been key to a lot of the success. So the question ends up being, where is our sort of transformer? Um, Again, I don't think we're there yet. I'm not sure exactly what would be the best model. It really depends on whether you're working with 2D graphs or 3D 3D structures. We only focus on 3D structures, and I guess what I'm arguing here is we pick the model that we think is good enough. So the GemNet model has been used, in multiple different domains like small molecules, materials, even proteins. I've seen applications of it. Um, and on the other hand, it's been scaled up to 1 billion parameters. So it's shown good scaling sort of performance. And it's also been, used on different properties. So that is, energy and force prediction that you would have in like an OC20 type of data set, and also the type of task that you have in QM9. So we essentially just end up using GemNet, and we think it's good enough. Second is the 2D versus 3D problem. Obviously, the 2D case is appealing because of there's a lot of issues you don't have to deal with. You don't have to deal with having fully sort of stable or equilibrium structures as input. You don't have to worry about uh, having a complex model that can handle these sort of geometric interactions in 3D space. Um, but this, I don't have a lot of intuition on really what would be the best method. I know I've seen methods that sort of incorporate both and try to do some sort of contrastive learning across the two different modalities. Um, we do 3D for everything here. And uh, that's partly just, I guess, the group that I was working in, and we work with a lot of 3D data sets, but also I think the other way I look at it is we want to maximally leverage the available data, and there's a lot of data available if you're working in 3D space. Um, okay. Another sort of non-challenge, and by the way, when I use this symbol here, I'm sort of talking about these sort of non-challenges, is the availability of data. So one key sort of uh, um, a factor to the success of, let's say, natural language processing has been uh, uh, availability of huge amounts of text. So I think Common Crawl last I checked prior to this presentation, I think it's 10 petabytes of data, and it's just unstructured, just sort of scrape data from the internet. Um, in in chemistry, I guess these data sets are much more expensive to generate than having to, than just going and scraping every page that you find online. Um, but I think um, large data sets do exist, and I think this is one of the main reasons I'm sort of considering this a non sort of blocking challenge, which is if you look at the Open Catalyst 2020 data set, that is 10 million training examples. That's in the catalysis domain. The Open DAC 23 recently they released 40 million. Open Catalyst 2022, these all three are from the same group, but overall you're looking at about 250 million examples from those three data sets. And there's a lot of other ones. PCQM4M V2 has been used a lot for pre-training. That is 4 million sort of stable structures. Transition 1X and A9 1X are two data sets that we use as well. That's about 15 million training examples, those two combined. So overall, we have a lot of data available. And when you compare this to, let's say, ImageNet, which fueled a lot of progress in computer vision and has around 15 million, 14 million images, um, I don't I wouldn't say that we're far behind in data. I think we do have a lot of data available. I think the real key question ends up being how can we effectively leverage this data that we have available to us? And I think one good way to think about this is if you're somebody who doesn't care at all about catalysis or materials, how do you leverage the 250 million training samples that is provided across the Open Catalyst data sets and the Open DAC data set? And does leveraging that data and in some sort of pre-training sort of framework, does that actually help for your downstream task? And I think that's sort of what we try to answer here. One thing, just a side point that I want to put out there, I think it's an interesting observation, is that one consequence of this limited data ends up being what comes off to me as overfitting, clear overfitting in some different data sets in this domain. And so if you look at some of the domains that were not listed in the previous slide and don't have a lot of data available to them, if you end up actually looking at sort of the models that are state of the art for those, you see that they do well on training data, but don't generalize to new data. I think the way you see this is large models end up basically overfitting on these small data sets. And essentially what you get is state-of-the-art models are smaller. And if you increase the number of parameters, you get worse performance. And I think, so what you see here, this is the RMD17 data set. This is an energy force, like molecular dynamics type of data set. It has 1,000 train examples. And so on the smaller side, and what we see here is four different models. The two up here are state of the art, and these are the GenOC models that we use as our backbone. All are trained from scratch, and you just see, first of all, the number of parameters of the state of the art models is 3 million and 7 million. And in our case, our smallest model was 30 million parameters, and then 250 million for the largest model. And essentially, here this is MAE, so higher is worse, and it almost looks like as you increase the number of parameters, the performance gets worse. And I think this is a worrying trend, potentially, because if you really want to replicate the type of success that we see in NLP and CV, effective model scaling has been a key in that domain. So I think it is imperative that we develop effective model scale, like figure out how to scale these models to larger and larger parameters. And I guess sort of a spoiler here, I think pre-training could be a way that we could do this. Um, so what is a challenge is the diversity of the chemical space. So I think if we have everything from small drug-like molecules to large proteins, inorganic materials, it's sort of metal organic frameworks, so on and so forth. This is huge variation in composition, size, and properties. And I think if we assume, as I mentioned in 2 slides ago, that we have enough data, that there's a lot of data sets available, we just need to know, we just need to learn how to use them, then I think that makes this the key bottleneck of the challenge, which is if we have a lot of materials and catalysis data available, then we need to figure out a way that can actually sort of you know we need to prove or find a way that pre-trains these learned representations and shows that these learned representations are transferable across domains. And just to go over this diversity, so what I'm showing you in this figure here, this is the set of pre-training and fine-tuning data sets that we selected for our work. Um, and just to go over, the diversity that we see, it's smallest data set has 600 samples. The largest data set has 210 million samples. Um, you go from all different kinds of chemical domains, small molecules, catalysis, large molecules, materials, um, different elements. I think overall there's about 85 unique different elements in these data sets, different system sizes, all the way from 3 or 4 atom systems to 500, extremely periodic materials sort of systems. Um, all different kinds of properties, energies, forces, band gaps, magnetic moments, binding affinity, so on and so forth. And so I think transferability is essential. Can a model that is pre-trained on OC20 that has energy and forces in catalysis, you know, can that be transferred over to a different domain that has a completely different property, let's say QMOF fatty apps, and has much less data available? So again, let's take inspiration from other domains. And this, so the key idea here is to learn shared representations that is useful across sort of these different modalities. And I think one area that really inspired us is multilingual language models. So this is where you have, let's say 50 different languages, so on and so forth, and you want to train a single language model instead of, let's say, one alternative would be train one language model on English, one on French, so on and so forth. The other one would be you train a single language model on everything. Really the trend has been, and I think this is the case for GPT and all of these other models, that multilingual language modeling is really the way to go. And essentially, these are some of the first papers that really kind of started working with this. Now, BERT is a pre-training paper, but actually, I don't know, I don't think they ever published this as a paper, but multilingual BERT was modeled that they trained after BERT. And the idea here is that you have a shared encoder in the model, and you essentially, you increase your vocabulary to allow for, basically these transformers take word embeddings, and so you have word embeddings for every single language. So you have a much larger sort of vocabulary. Um, and if I recall correctly, most of these models have a per language decoder. So it's a shared encoder per data set decoder. And most important part is what I've bolded here, which is their data set didn't contain any sort of cross-lingual data or objective. And that is to say, um, when they sample the batch, let's say every element within that batch has only one language. There's no alignment data that says this is, like translation or something like this that actually helps the model connect the different embeddings. All you're doing is sort of you're bottlenecking the training such that you have a shared encoder. And this is sort of fairly consistently, this is shown. So BERT was one, XLMR was another one later. Consistently, what you've seen is these multilingual models do better than monolingual models, especially on lower resource domains. There's some, at least originally, I'm not sure where it stands right now, but for English, because the majority of the data is in English, I think originally there was some drop in performance for English, but basically for all other languages, you end up seeing better performance. And I think that's really what we're looking for in pre-training.
Can I
Um,
ask a quick question here?
yes.
I'm most familiar with this literature. You could picture that there's something intrinsic about like human experience and language that is capturing like a fundamental concept of a cat is the same across languages. And so that is where the shared parameter efficiency comes from. But you could also picture that there's some like intrinsic thing about a trained neural network that leads to some sort of spectrum of in the layers that is kind of independent of whatever task you end up training it for. Like, could
No.
you see benefits if you train it for, on something that would be totally unrelated to language, but it's just training a neural network with stochastic gradient descent, sort of preconditions the network to be kind of in kind of a state that is better than what you would start with in initialization.
Yeah, no, I think that's an interesting question. I don't know if I have the uh, intuition for which I think is the case. I do know of a paper, although I'm somewhat skeptical of the paper, but this was a few years ago. It's called uh, I think it's large language models or universal computation engines or something like this. And this was where they took a pre-trained language model, I believe it was GPT-2 or BERT, one of those two, and they fine-tuned it on image classification. And as a matter of fact, they they didn't fine-tune the entire model. They only fine-tuned, I think, layer norm weights, which is like something along the lines of 5% or less 0.5% of the weights. Layer norm weights are generally fairly small. Um, and they were able to get something like 99% performance on MNIST by doing so. And so what they argued in that paper was that during training, there's interesting computation primitives that these models learn, and that and that's sort of what they're able to utilize. I think there's some merit to that potentially, but I I'm not quite sure which I guess you know uh, uh, I don't have an intuitive feeling on which is the case. I'm more inclined to say that it is sort of the former of what you explained, which is that it is learning similar concepts of what is a cat amongst the two different sort of uh, uh, you know uh, two different languages. But yeah, I'm not quite sure on that.
I guess could you probe this by asking like how similar of the data sets do you need them to be in order for it to get this benefit of pre-training? Or alternatively, if you make your decoders very, very low complexity, like linear decoders, rather than like, does that help try to identify whether they've intrinsically learned concepts versus just having some sort of sort of joint representation space that's better than like one of these universal compute engines.
Yeah, no, I think so. And I think Well, so in our case, the decoders were, for the most part, simple. They were MLPs and not just simple linear probing. But I do agree with you, and I think I've also seen. I think there was a recent paper in NeurIPS this past NeurIPS, that essentially trained a single force field model on everything. And so in that context, that is they didn't actually have separate decoders. They essentially took a bunch of different data sets and they said these are all energy and force data sets. Um, energies are tough to deal with, and I'll talk about this later. But forces are just forces, and so they just had a single force output head.
Okay.
I think that one's interesting, and I think maybe suggests that there is some interesting similar embeddings that they're learning. And then the other one that I'll say as a final thing is one difference between what we'll be doing and what they're doing in NLP is the way we sort of are creating these node embeddings or atom embeddings. So in natural language processing, you do a tokenization, and basically, essentially, every word becomes a sort of token, and that becomes an embedding. Whereas in our case, we do already have the sort of, the atom. And so if you're looking at Open Catalyst project data set that is, some catalysis, if that has a carbon, that carbon embedding will still be the same embedding in QM9. And I think so that probably helps it more to learn maybe interesting, useful features that are transferable.
Awesome. Thank you.
Yep. All right. So second, in speech, there's a very similar kind of idea. These are multilingual speech models. And actually, this is almost exactly the same story that you see in sort of multilingual sort of NLP. And single shared encoder, no cross-lingual data, and language-specific decoders. And this has sort of been a formula that's worked quite well. So what we think is that such a strategy could work well in the chemistry domain. So learning shared representations across chemical domains, molecules, catalysts, proteins, so on, and by having a shared encoder and dataset specific decoders during pre-training. And then for fine tuning, we don't even use those dataset specific decoders. We'll just throw it away and we instantiate new decoders. And obviously, I guess the theory is that this would enable more effective transfer learning, especially for these low data domains. So I'm going to take a little bit of a detour before talking about the sort of final challenge that I find to be an interesting one, at least, and talk about DFT. So I'm not by no means an expert, but my high level intuition on sort of I guess what we did in Open Catalyst and generally this process is, let's say we're interested in some property of interest in a molecular system. A lot of times to actually be able to get that, so in OCP, that would be the sort of total energy of the system that then we would use to compute the absorption energy. We need to know the full ground state equilibrium structure of the system to be able to compute these. But usually what we're working with is new sort of materials, new molecules for which we do not know these equilibrium structures. So to first be able to even do this computation, we need to do some sort of geometry optimization, relaxation process. And DFT is one of the ways that this is done. Essentially, what we end up doing is we make an initial guess of these atomic positions using some heuristics, plus I'd imagine some randomness. Again, this is I'm trying to paint a very high level picture of this. Then we compute the forces on atoms, and this is where DFT comes into the picture. It sort of computes the energies, and we can take the gradient normally. And then we kind of, this is your average sort of optimization procedure. So you can just optimize the positions to minimize the forces, and then you continue until some convergence on the forces. And what you see is that process right here. So this is a specific reaction that is of interest in sort of fuel cell in the fuel cell reaction. And what you see is that, so in the background, or this is like I guess these are the catalyst that is sitting in the background and the molecule that is sitting on top of the catalyst. And at the beginning, you see that is sort of our initial guess, and the relaxation process is this sort of video. What you get along this trajectory is a lot of non-equilibrium structures that you have to sort of generate or compute as you're sort of doing this optimization. I think it's in the case of Open Catalyst, it may be, even up to like 500, anywhere from tens to hundreds of these non-equilibrium structures. And an effective pre-training method should be able to utilize these non-equilibrium methods, given how many there is. So when I talked about Open Catalyst project being 210 million, these are not 210 million stable like equilibrium structures. Those are 210 million optimization frames. I guess where I want folks to be thinking about is the amount of information that is stored in these sort of intermediate frames, and how can we effectively utilize this. So this is what I'm sort of calling the non-equilibrium problem. So this is the way I've presented this is a bit of a sort of meta take or like a nuanced take on this. So when you think about traditional ML of natural languages and processing and computer vision, what you have is a large corpora of what I'm calling natural input data that have noisy or no labels, noisy labels or no labels whatsoever. By that, what I mean is, if you think about natural language processing, when you look at, let's say, the archive papers data set, those are all naturally occurring, like actual valid sentences. They're not non-equilibrium structure of sentences with half random words and half, like some linear combination of that. And similarly in vision, when you take these images, it's not like you have a half noisy image. I'm sure there will be some of those, but the data set is all naturally occurring images. Um, while these data sets, we don't have good labels, but we have good inputs. And so, and this input data itself is representative of the sort of distribution that we care about and we want to model. These traditional self-supervised learning methods were designed for learning this natural data distribution. When you think about denoising or masking and so on, it really relies on that input data having enough signal for you to be able to actually reconstruct the masked parts. Um, and Okay, so if you now go to this domain, what we instead have, and I'm specifically focusing on these DFT data sets. I'm sure it could apply to some like maybe molecular dynamics or so on. But what you have is mostly unnatural, and by that I mean non-equilibrium input structures, but the predicted energies and forces are actually fairly information rich, potentially more information rich than the input itself. And so this is a slight difference that we see between these two domains, and I think this to me kind of also motivates the potentially what we should be thinking about in terms of our approach. Um, so um, okay, and just to give some numbers here again, in OC20 we have less than 1% of the data is or actually less than 0.3% of the data is equilibrium. So 200 million versus 640K. And so, okay, the application of these SSL methods to unnatural data settings is non-trivial. I think it could be done, and I think I'll talk about it at the end of the presentation. There's interesting work that could be applied, but it is non-trivial to just take an existing method like denoising and use those on non-equilibrium structures, because those are already sort of kind of noisy. And again, the analogy would be training a masked autoencoder on an image that's 95% noise.
Can I ask a quick question? For the OC20 set, do they give you the forces for the
Yes.
non-equilibrium structures?
Yes, that's correct. And this is what I meant by the sort of reliable labels. I think those forces are fairly useful, and throwing those away seems like a waste. And yeah. So what you end up getting because of this non-equilibrium problem is many of these SSL-based pre-training methods, the ones that are at least in sort of 3D space, because in 2D I don't think you really have this problem. They only use equilibrium structures, so I'll talk about some of the one of the like very interesting works. This is from DeepMind, denoising via pre-training via denoising paper. They use the PCQ M4MV2 dataset, and that is equilibrium structures. I haven't seen as much work on sort of using non-equilibrium denoising. So the real solution here ends up being finding some way. And what we argue is let's just go back to basics, supervised force field learning as a pre-training objective. So this is where sort of the direction of this work sort of was headed. So going through previous approaches just as a high level overview. So on the 2D side, I think of techniques like Grover as very similar to what you see in sort of like BERT and masked autoencoders that I spoke about previously. So you have contextual property predictions such as masking nodes, masking subgraphs, so on, and predicting these structures. And they also have some graph level motif predictions that they sort of kind of becomes like a additional sort of supervised learning task on top of it. But the one that I was just talking about in the 3D domain is this pre-training via denoising paper. So this is akin to these denoising autoencoders. I think this figure does a fairly decent job. You add noise to atomic positions, and you have a graph neural networks that predicts that noise. And that's sort of the denoising product. So what they talk about in their paper that I think is interesting to think about, in their sort of theoretical description of why they think this is an interesting method or why this works, is they talk about how denoising autoencoders can be thought about, or can be formulated as a particular type of force field, and that can be cheaply evaluated. And what they argue basically is in cases where DFT is very expensive to do, um, instead of using the DFT force field, you can essentially end up using this cheap force field of adding sort of some Gaussian noise and predicting that Gaussian noise. Um, and this is definitely interesting, but just a note here, the data set they pre-trained on, the PCQ M4M V2 data set, had to use DFT to generate the stable structures that they pre-trained on. So essentially, to me, it's unclear how much computational savings you get from taking stable structures that you had to predict using DFT, and then you use what you like, I guess, something that you're calling as an approximation to DFT force fields as your pre-training objective. I think this could definitely be useful in cases where we have, again, some idea, maybe much larger systems we can't do DFT on, and so we have to do something. Yeah. So, but I think that ends up being the connection between sort of their method and ours. I think they're both ultimately really some kind of force field prediction. So, with all that background out of the way, so this is where we get to the joint multi-domain pre-training. So, the key idea here is that essentially we pre-train on diverse data from different chemical domains simultaneously. And this is very much inspired again by multilingual NLP. I think if you take a look at this figure, we're showing the 4 data sets that we use for pre-training. We picked catalysis and small molecules as the domains for pre-training that we trained on. I'll go into details later. But all of these sort of get concatenated into a large data set. They go into a shared backbone model. So that's this right here. And then every data set has its own data set specific output heads. Okay. And and I'll go into details with these later, but the shared backbone model is really what we're interested in keeping. And when we go to downstream and we want to sort of evaluate this model, we throw away all of those existing pre-training heads and we fine tune on the data sets of interest. So pre-training, we trained on a mix of 4 different data sets over different sort of chemical domains. That's about 120 million trained samples in total. Notice we're not using all of OC20. We actually subsampled OC20. The way we picked this was we subsampled OC20 such that our full data set is the size of the trained set of OC20. This made it so that in some of our ablations, we also didn't have to train another model completely from scratch, and we can train to just a model pre-trained on OC20 only, which is a very useful ablation to take a look at. So our pre-training objective is energy and force prediction. Technically, OC20 provides absorption energies. So you have to do some work to actually sort of remove their absorption energy referencing and then get total energies. We wanted to make sure every single data set used total energies as their training objective. Then we did a technique called linear referencing, essentially a data normalization technique. What it gets to is training on energies is a bit complicated. These energies are DFT computed total energies are effectively sort of arbitrary. They differ based on what functional you use or what DFT settings and software and implementation. And so you need to essentially reference these energies somehow and normalize them. And so we had we used a common technique across all of these called linear referencing. This is a per atom reference that we compute and we subtract from the energy for every system. Then the normalization for forces is these are all fairly standard to divide by the component-wise RMS. And then finally, we used a technique called temperature sampling. This is fairly popular, so I'll just jump to this. This is a fairly popular technique in multilingual NLP. The idea here is actually, if I go back, if you look at our data sets, you have 100 million for OC20 and 2 million for ANI. If you sort of just concatenate these data sets, OC20 is going to dominate the training. So we kind of want a way to balance these out. And temperature sampling is a way of doing this. So you have a hyperparameter called T, and you essentially sample with this sort of probability that I've mentioned over here. So here I've just shown pie charts for what the distribution of the data looks like as you adjust T. So T equals 1 doesn't change the data set at all, and the majority of our data is OC20. If T equals infinity, you get fully balanced sampling. And what we picked was T equals 2. And that gets some more sampling and still oversamples OC20. Um, and there is other work on this. Actually, one of the reasons we picked T equals 2, there's a work in multilingual NLP that sort of shows, in that context at least, that going from T equals 1 to T equals 2 helps. Going from T equals 2 to 3, 4, 5 doesn't help as much, or it's much more marginal. Model backbone is GenerateOC. Again, I think I already sort of motivated this, but it's been used across many different data sets, OC20, OC22, MD17, MapBench, PubChem. And it's been shown to do well on very small data sets like MD17 and also on very large data sets like OC20. And it's been scaled up to a large number of parameters. There was a paper that scaled this up to 1 billion parameters. And it was, it had a sort of the type of scaling that you'd hope to see by increasing the number of parameters. So, okay. So for the multitask retraining, we have a shared backbone, that's GenerateOC. Then for every single data set, we have a separate prediction head. So that's what you see over here. OC20 has its own energy force head, transition 1x, so on and so forth. This is again, this is why we kind of call this multitask learning. Every data set essentially becomes its own task within this multitask framework. The model is trained on all these data sets simultaneously. That just means that we create a combined data set and we sort of treat it as if it's as if it's all a single data set. But during the training, what we have to do is essentially, when we compute the loss, we have to make sure that we take the right output head. So there's some details of the implementation that you have to make sure. Basically, for computation reasons, all the output heads are always running in parallel. But once you compute the loss, you select the right one to actually add to the final loss. The motivation, I guess what we're hoping is the backbone would learn generally useful atomic representations and the heads would learn specific features to the task. So this plus the normalization that I mentioned are sort of how we're dealing with the different complexities and the differences between these data sets. Okay, loss function, this is fairly simple. So you use a mean absolute error for the energies. These are all fairly standard for force field learning. And for forces, what we use is the L2 mean absolute error, and just sort of like the L2 distance. The only difference is, and this is what I'm showing in green here, is you have to be careful about how you do the reduction of your force loss. So usually what happens in a lot of these sort of GNN type of frameworks is force losses are averaged at a per atom level. But what we do instead is we average them at a per atom per structure. So it's like two different sort of reductions that are happening. And the way you can think about this is, imagine if you have a batch that has a sample from A and I that has, let's say, 5 atoms, and then a sample from OC20 that has 120 atoms. If you do a per atom reduction across the entire batch, OC20 will dominate that loss. This helps actually account for that. And just as a sort of, again, another spoiler, adding this was the most important ablation to our results, in terms of making sure that these are balanced. And then for fine tuning, fairly simple. You just throw away the output heads for the pre-training and add new ones. Keep the backbone. We train the entire model. I know there's some parameter efficient fine tuning or linear probing, things like this, where you don't train the entire model. I think that's for future work. But in this case, we train the entire model using a smaller sort of learning rate, fairly standard for this kind of literature. Okay, so for the results, one thing I'll say is, again, taking inspiration from NLP, I think it's important that we do have a diverse benchmark. If we just, let's say we picked small molecules and we pre-trained and fine-tuned on small molecules, maybe we, we're not assessing generalizability in a way that I think we should be. And so I compared this to glue and super glue and NLP, and they essentially, it's a similar kind of thing. They took a lot of different NLP tasks of interest, like question answering, sentiment analysis, so on. And if you wanted to show that you've created a good pre-training method, um, you would show your results on all of them. And that's how you can show that this is a sort of generally useful or good method. Uh, so we develop a benchmark that spans a wide range of chemical domains, levels of theory, and properties. And I think so what you see over here is you have MD17, for example, and MD22. These are molecular dynamics, and SPICE. So you have energy and force prediction, which is what we had in the pre-training data set. But you also have property prediction, and like QM9, MapBench, QMOF. And you also have a lot of different domains, so materials, large molecules, small molecules, so on and so forth. Okay, so for experiments, I guess one thing I did want to mention here is in the data set, we made sure to have a sort of ID/OOD kind of like split of what we consider pre-training and fine-tuning. So that is happening in two different axes. One is the chemical domains that we worked with. The reason we only did catalysis and small molecules for pre-training was because we could have there were large like materials projects on data sets that we could have included. We wanted to have a split of what we would consider data that is not included in pre-training and is being evaluated in during the fine-tuning sort of stage. So large molecule systems are not present in our pre-training data, and the materials are also not present. I guess MapBench, one caveat, the catalyst systems that we do work with, there will be some similar kind of periodic material system, but the type of reactions that they're working with are going to be different. And I think the metal organic frameworks, that's also something that we don't really have in our pre-training data. So that's one axis. And then the second one is the axis of sort of labels and ID. So ID and OD in that context. So everything in our data set for pre-training is energy and forces, but for fine-tuning, there's a lot of different properties of interest that we're working with. Finally, model variants, we have a large model and a small model. That's 250 million for large and 30 million for small. Okay, I'll go to the results. So I can, I'll go fairly quickly over these, and if folks are interested, we can come back. But for the most part, we were extremely sort of pleasantly surprised to see the, I guess, the generalization abilities of this model, and the fact that it just did well on every single domain that we sort of played around with. So on QM9, that this is sort of small molecules, equilibrium structures. We essentially for all except this, I think this is the electronic spatial extent, that this is one that we didn't get the state of the art on. This is a figure where we're comparing to other pre-training methods, and so relative improvements from scratch of these existing pre-training methods. And again, this is one where we're able to show a lot of improvement. MD17 is one where we traded blows. This is a much smaller data set, and it's one where the type of models like Mace and Allegro that are sort of these equivariance, Fricker harmonics-based tensor product models do extremely well. But we definitely did very, I think it's 5 out of these molecules that we set the state of the art on, and a huge improvement over training from scratch. I think that's one thing to keep in mind. Same thing with the macromolecules sort of data sets. The SPICE data set doesn't have a lot of models to compare against, but I think MD22, by the time of the sort of publication, there's a lot more models to compare against. And I think we're doing extremely well in that domain as well. Then materials, sort of similar deal. I think the model does extremely well, even compared to other pre-trained methods. In the case of QMOF, these two are also pre-trained. The final one, we only did this during the review process. Somebody had asked for trying things on MoleculeNet. I'm not very familiar with this data set, but MoleculeNet was fairly easy to set up. And this was one that we were able to do quite well on. And without really, this was during the week of getting the reviews and having to respond to it. I'm sure we could do more here and explore these results a bit further. Um, I also want to try on other versions. By the way, I think this one was the only one that I was able to fit into memory, the entire 3D structures. And we already had to use a lot of tricks to actually do that, gradient checkpointing, so on and so forth. But um, then the ablations, I think the main one that I'll say is higher temperature is better, but the marginal improvement is past t equals 2 is, or the improvement past t equals 2 is marginal. And there's a paper, the first one here, that basically says the same thing in the NLP domain. Higher regularization better. Look at number 2. This is also literature in other domains that confirm the same thing. Multi-domain pre-training is critical. So this one down here. If you just use OC20 pre-training, it does 10% worse than base. And really, our methodology is this one over here, the 13%. And then the specialized multitask optimizers like PCGrad, these are ones that compute separate gradients for every single task, are not really necessary. They don't really hurt or help our results per se. When we compare it to this SWL. Okay, so final sort of bits of analysis that I just want to share here. That this is sort of like an aggregation of all the sort of all the findings is using this pre-training improves downstream performance. This is us comparing our model trained from scratch versus the fine-tuned model. And this is a 59% on average improvement in the performance when using this model. This is the more interesting one, which is pre-training combats overfitting, essentially. And so what we show on the left here is when you take the scratch model, the small version, and you go from small to large, what is the relative difference in performance that you get, or improvement in performance? It does 8% worse on average. That's sort of indicative of overfitting. And then on the right, what we see is when you use pre-training, you do 21% better when you go from the base to the large model. And then finally, pre-training takes a while, but it also leads to much faster conversion. So in this case, we took the converged performance of all of the scratch models, and we looked at how long it takes our pre-trained models to get to that same level of performance, and I was able to reach that in 1/12 the time. So this is that's the end of it. We proposed this multitask pre-training. We think it improves generalization, enables scaling to larger models, and we think this is a very interesting direction to move forward to. These are some interesting future directions. Feel free. The slides should be online, so feel free to take a look at these. If there's any questions, I'd love to take it.
Awesome, thank you. Any questions?
Hi, thank you for the talk. I have a clarifying question. So when you're pre-training, you're only predicting the energy and the forces for different the pre-training data sets, and then when you fine-tune, you have a bunch of other properties that you want to predict for. So do you fine-tune on like a single data set at once?
Yes.
And then is it like a lot of work to add the prediction for all those other properties?
No, I mean, so we essentially, when we don't do a joint fine tuning, it's only a joint pre-training. In other words, when we're fine tuning, I think we fine tuned on somewhere like 40 tasks in total. That is 40 different models that we fine tuned. So each one, it's a separate model.
So like even for the same data set, like each property is going to be a separate model.
Yes, exactly.
Okay.
That's generally, I think, how most in most of these data sets, that's usually what all the other state-of-the-art models do as well.
Okay, because I was imagining like for each data set you had like multiple properties, like you would train the model, you fine-tune the model to predict all those properties at once, but I guess you do it one at a time.
I think that's an interesting direction, and well, I know it has been explored, not even outside of the pre-training fine-tuning sort of context, which is just multitask sort of models on QM9 and so on. We tried to stay fairly focused in this work, but I do definitely think that's an interesting direction to follow.
Okay, thank you.
I have a, I have a quick question about you alluded to this a little bit, but most of these structures that you're training with are not like they're generated from MD or a DFT or something like that. And I'm wondering to what extent your model is, and these kinds of models in general are sensitive to how the input structures are prepared and whether if it's generated with a different software package, does everything break, or is this something you have to account for?
Um, so we didn't carefully explore this. The only thing I can mention is the four data sets that we used, every single one of them had slightly different sort of settings that they use for DFT. OC20 and OC22 have slightly different settings, but obviously they were both using the same software from the same, coming from the same group. But ANI 1X and Transition 1X, I think they come from a completely different, different groups and use different functionals and so on. So um, I do think our results do show that if you do the normalization sort of things that we did and you do this sort of per data set decoder and so on and so forth, that you can deal with the differences in the sort of DFT functionals and so on. I think otherwise the model wouldn't have been able to do this kind of generalization.
Gotcha. Thanks.
More questions? I have a quick question. So this is really exciting work. I think it's great to see just the raw performance that you're getting out of it. And also the methodology, I think, really speaks to how the field should move forward. So I'm completely agreement. I'm curious on to the extent that your work here speaks to some of the scaling law type of work in this area in terms of are we now limited on like if you now that you've scaled the data bigger and you've seen that you can increase the model size and not overfit as much, what's the next axes do you think that really we can push on, or is it compute, model size, and data all together? Or there's room for growth in all directions?
Yeah, I mean, I think we already have what it takes. It just takes some engineering effort probably and time, but to really like go to multiple billion parameter models with the data sets that we already have. I think there hasn't. I think it would be interesting to have like a kind of like a scaling laws, like the original scaling laws paper in NLP that sort of shows that. But from what I've seen, at least in the OC20 data set and some of the models there, we are seeing a similar kind of like a power law type of, as you scale up data and compute or data and parameter size, that you get better and better performance. So in that context, I think that's obviously somewhere that we can push and maybe get some predictable amount of performance out of it. The other area that would be interesting to me is, we very much limited the study to, not training on all the data available, creating ID, OOD. At some point, I also think it is worthwhile to just go all out and basically take all the data that is possible and then think about how you want to merge it. I don't know if this methodology would be one. There's other methodologies where, you know, like imagine if you take the same molecular systems and you use a couple of different DFT functionals and you actually now have sort of cross lingual data that I was talking about in NLP that doesn't exist. We can also create data sets that do that kind of thing, and so there's a lot of interesting directions to go there. Uh, I think there's a lot of obvious ones, I guess, that I've mentioned here.
We have time for maybe one more quick question if we haven't. I guess if you have time for one more, most of these data, to follow up on Henry's question, are on computed. To some extent, you could call these synthetic data sets because they're simulations. I'm curious if sort of a similar type of effect you would see if you were dealing with experimental data sets. I guess to some of your fine-tuning ones are experimental. But is there a qualitative difference, or is this a route that you can picture of going towards, generating more and more data just by running the simulations? In some senses, is can be less less costly than some experimental measurements.
Yeah. So I think so. I think that the best so during pre-training, what I personally think is um, the I think JUMP is a very basic, sort of straightforward implementation of basically multitask supervised learning. What I personally think, and this goes back to sort of the future work that I mentioned, is um, I think self-supervised learning will be useful. And this is getting to the question, but I think a combination of using all the force data that we have available, plus, let's say, some sort of SSL methodology. So DENS is one that I mentioned here. This was a recent work where they essentially create a formulation for denoising on non-equilibrium structures. Um, and so that's one direction, but also one that, let's say for equilibrium structures, you do denoising, and for non-equilibrium, you do DFT or something like this. So if you do that, what I would imagine is for these sort of equilibrium structure, or for these experimental data, as long as we have those equilibrium structures present during pre-training and we do some denoising on them and so on, that at the very least the model will know what it's working with. And so I think that could potentially be useful. Obviously, in those cases, there's a similar problem, which is what I mentioned. You need to do DFT for a lot of these to have an accurate understanding of what the structure even looks like in 3D. So I think as long as we do have that, and then we can do some denoising or so on, I think that could definitely generate better performance, especially I would imagine for these kinds of experimental data.
Awesome, thank you. All right, well, we're absolutely thrilled to have you share this work. It's really impressive, and it's great to see that this bringing in a lot of the big ideas from other areas of machine learning towards this task is, I think, going to really push things forwards. So thank you so much, and congratulations on this really nice work.
Thank you very much.